In this demo, we will analyze a VLC media player exploit by doing timeless analysis using reven. Although the example is fairly simple, it will allow us to cover the main features of the product and see the contrast with more usual methods. As a matter of fact here, one way to approach the example would have been debugging the program, trying to work your way backward from breakpoint to breakpoint by restarting the exploit between each step, until of course we get all necessary information. But working with timeless analysis is different. We can record the entire virtual machine while it's running the exploit. And since traces tend to be huge on top of that, reven provides tools to find your way around. In this demo, we'll see how we can jump in the external binary back to the shellcode, then verify where the shellcode is coming from, see how the exploit sets everything up, and finally, verify the kind of vulnerability we're dealing with. Here is Axiom, and the first thing we notice is the instruction view in the middle. It represents the list of instructions that got executed during the trace along with the moment in time I'm currently selecting. So by doing so, I'm moving forward in time, and by doing that, I'm moving backward in time. And you probably saw a few widgets around that trace got updated. They represent the state of the virtual machine at the moment that is currently selected. For instance, in the frame buffer here in the lower right, we can see the state, of course, of the screen. And by jumping 14 million instructions in the future, the frame buffer shows me that the file dialog is being erased from screen. Now, if I want to see what happened during the record from a user perspective, I can use the timeline widget below. It is a representation of the trace from earliest instruction to the latest, and by clicking inside it, I can move forward and backward in time. So by zooming out the frame buffer and clicking, I can see the open file dialog got erased, then VLC read the file. It's pretty huge, it's about a gigabyte large. Then at some point VLC disappears, and then an external binary is executed. So let's dig in this trace, and one of the first things I'd like to see is where this binary is executed. There are a few ways to do that, but one easy shortcut is to use the strings widget. The strings widget is a view of dynamic strings in the trace. There are not static strings which would be extracted from the binary, but instead there are memory regions that got manipulated during the trace and that look like strings. So here there is a fair chance that we can find the string offensive con being manipulated. So let's search for it. There are a couple of matches because of course the string is being moved from place to place, but I'm only interested in the first string and the first access. And if I look at the backtrace, I can see that I'm inside a call to message box called by a binary called calc.exe, and looking at the frame buffer, I can see that at this point in time VLC had already disappeared, so there's a fair chance calc.exe is my external binary. But what I would really like to see is where it got executed. Again, couple of ways to do that. I could either search for a call to create process, or again I could search for the string calc.exe because it's going to be probably manipulated somewhere. So let's do that. Calc.exe, again there are going to be a couple of matches because someone is trying to execute this binary from various path, notably here from system32, but again I'm only interested in the first string, first access. Look at the backtrace, I'm inside the call to create process called from winexec. And what's interesting here is that I can see the backtrace cannot give me more information on the callers from winexec, and the reason is because here the exploit changed the stack. So let's have a closer look to who called winexec. By double-clicking in the backtrace, I can get to the point of the call, and by scrolling up I can see who called that. And obviously here, someone is trying to find the address to winexec. And since this address is strangely aligned, I'm guessing this is probably the shellcode I'm looking for. I can verify that. I can copy the address and open it up in the memory view like so. And it does look like binary code. So I want to taint that. I'll select the first few bytes, copy the address range, and ask the taint engine to taint that memory region from my current point in time backwards up to the start of the trace. And it's going to give me all the moments in time where the taint has been moved from place to place. In this case, I can see my taint went from a buffer to a ZMM register back to another buffer. This is a memcopy call. And the same pattern appears afterwards. And this is where the taint stops. So if I look at this call, I can see I'm in a memcopy called by ntread file. So my shellcode is coming from an ntread file call. But what I'd like to know now is which file is being read. Again, I can double click on the call here, and here instead of tainting the buffer, I'm going to taint the handle, because the first argument to an ntread file call is the handle. It's stored in RCX, and here, yes, this looks like a handle. So now I'll ask the taint engine to taint RCX, the first argument, from my current moment in time, again backwards, up to the start of the trace. What I will be looking for in the taint results here is the taint going through RAX, because when I created the handle, it got returned as the return value from a create file call, and the return value in x64 convention is passed through RAX register. So I can see the taint jumps back almost 3 billions in the past in a couple of seconds. And yes, there is an RAX match, so I select this moment in time, look at the backtrace, nothing interesting. But if I look up a little bit, I can see that RAX is coming from create file internal. So I click inside this call, use the backtrace to go to the start of the call. And again, I can check the arguments. The first argument to create file is a pointer to a string to the file I'm trying to open. I look at the CPU, RCX is a pointer. I open that up in the memory view, like so. And yes, this is the proof of concept file that I opened at the start of the trace. So here, in just 2 steps using the Taint engine, I was able to verify that the shellcode was coming straight from the file. Now, moving back to the shellcode, like so, I want to see how the exploit called the shellcode, and so I need to move back to the start of the shellcode. Here I can do that by checking where it created the arguments for winexec. The first argument to winexec is a pointer to a string that represents what I want to execute. So by coming to the start of the winexec call and looking at the CPU, I open RCX as a pointer, and I can see that I try to execute calc. So by selecting this memory region, I can display the entire history of memory accesses on this memory region. It will automatically select the previous access, so here by just double clicking on it, I can see who wrote that value. This is what I do. So here I'm back at the beginning of the shellcode, and we're just coming back from a call to virtual protect. This is probably the beginning of my shellcode. Moving up a little bit, we are obviously jumping inside kernel code, which I don't want to see, so I can just use a shortcut that when I select a ret is going to take me to the corresponding call, or in this case, the corresponding syscall. I do that. Let's scroll up a bit. Again, I'm inside the call to virtual protect, and back inside the VLC code. And it's instantly obvious that this is the rob chain back to the stack pivot. Now the question becomes, what vulnerability made it possible to call this rob chain? This dereferencing call is obviously not right. The memory region here is the same memory region that my exploit was using earlier, so this is probably controlled by the exploit already. So moving back this chain of references a bit, I am going to be looking for a pointer that is not coming from this memory region. So this is not it. Again, this is not it. This is the first pointer that does not come from a memory region that is obviously controlled by the exploit. RSI in C++ code is very often the this pointer, and we can check that it's true by seeing where RSI is coming from. And here it's coming from RCX, which is the first argument to the C++ call. So yes, here RSI is my this pointer, and it looks like I'm doing something like a virtual call which ends up in the middle of nowhere. So there is a fair chance that RSI, here the object pointed by the this pointer, is corrupted. There are a couple of ways an object can be corrupted, but one of them is obviously if it's a use after free. And it can be fairly easy to check here if I'm looking for a call to the destructor of this kind of object. If a destructor is being called on my this pointer before this moment in time, then it means my object has already been destroyed. So to remember the pointer I'm interested in, I will set a bookmark here by doing so. Object corrupted. I can select the type, and obviously here I'm interested in libmkv plugin, call to this type of destructor, and I start the search. I found one result which is represented here by this line in the timeline widget, and I can see it's just a moment before my current point in time. So I select this point, check the argument RCX, and yes, I can see RCX is the same value as the this pointer we had before. So this is indeed a use after free. So just to summarize things here, we've been able to jump inside the external binary, back to the shellcode, verify the shellcode was coming from the file, we saw how the exploit set everything up, and finally we checked that the vulnerability here was a use after free. Thank you for watching.